Hello everyone. Here, I am going to introduce my recent work, Chronos, a testing framework for detecting timeout bugs in distributed systems by deep priority fuzzing with transient delay. Distributed systems are prone to various faults that may occur at runtime. One of the most common faults is delays, which can be caused by uncontrollable factors such as network traffic, resource monopolization, software bugs, and so on. In complex distributed systems, to mitigate these unexpected failures, various timeout mechanisms have been proposed, ensuring the stability and reliability of distributed systems. When object O1 sends a request to another object O2, O1 sets a timeout value and waits for the response from O2 until the time expires, in case O2 fails or a message loss occurs. O1 can break out of the waiting state triggered by the timeout event, execute timeout handling code, and take proper actions, retrying or skipping accordingly. In general, the timeout mechanism in a distributed system mainly distributes on two parts. Components interact locally through local I/O, and nodes communicate remotely via network I/O. Distributed systems are inherently complex, involving numerous resources and nodes that communicate with each other to handle unexpected delays and maintain uninterrupted service provision. These systems require a significant number of timeout mechanisms. However, due to this complexity, it can be challenging to avoid incorrect handling or implementation bugs in these timeout logics, which we call them timeout bugs. To effectively test these timeout mechanisms, it is necessary to trigger more abnormal delays than those occurring naturally during regular use by injecting plenty of delays. Here I show an example of timeout bug in HDFS, where incorrect handling of the timeout mechanism led to critical issues. The data streamer throws an I/O exception and incorrectly sets its state to interrupted, as shown in line 18. However, when the thread then performs other actions, such as an RPC remote procedure call to name node by the function abandon block, it first checks the current state and fails immediately since its state is interrupted, triggering this bug. This bug obstructs the RPC to other nodes, causing service hang-ups and affecting the availability of the HDFS. However, there are three main challenges. First, code implementation of distributed systems is huge and various. It is hard to precisely identify all the code locations where to inject delays. The second challenge lies in effectively triggering instrumented delays in deep paths, where timeout bugs tend to remain hidden. In distributed systems, the business logic is usually divided into multiple phases, each with its corresponding timeout mechanism. Frequently executing delays at the shallow execution paths prevents exploring timeout mechanisms in deep paths, resulting in ineffective testing. The third challenge is that executing delays will introduce significant overhead to the testing process. Since actual timeouts are usually time-consuming, directly inserting delays reduces testing speed and consequently testing performance. To overcome these three challenges, we propose Chronos as shown in this picture, which consists of two main processes. The first process is the delay instrument process. In this process, given a DSUT, the delay injector first decides where to inject delays, then precisely injects the fine-grained delay logic, and finally, outputs the instrumented DSUT with a set of delay blocks. The second process is the testing process, which involves the following steps. Chronos first loads workloads to send requests to the distributed system. Then delay selector dynamically selects a subset of the delay blocks according to the runtime context, such as call trace, execution depth, and so on. After that, Chronos combines the selected delay blocks and generates a delay sequence. And then delay selector activates all delay blocks in the sequence. DSUT executes the workload with the activated delay blocks. To speed up the testing process, the delay executor proposes the transient delay mechanism to quickly trigger the timeout mechanisms. Finally, the timeout bug analyzer monitors the runtime states of distributed systems in real time and identifies if there are node crashes or service hangs. The timeout bugs are reported once they are detected. Chronos proceeds to the next iteration, from step 1 to step 7 of the testing process until termination. First, the delay injector determines where to inject delay, which code locations in delay blocks are eligible to inject delays. There are 3 alternative delay injection methods as shown in figure. First, we can directly modify the source code of the distributed system under test. However, it is hard to identify all timeout mechanisms since their code implementation are complex and various. Or we can inject delays in local I/O and network I/O by the Linux kernel. However, it is hard for the OS kernel to distinguish which caller, which delay blocks D1, D2, or D3 calls through the I/O. Since timeout mechanisms in local interactions and remote communications are executed through local I/O and network I/O, usually, distributed systems do not directly operate these I/O but rather utilize existing common runtime libraries, so we can inject delays in the runtime library layer. The second challenge is to decide when to activate delays. Each delay block has 2 states, activated or deactivated. Because there are so many delay blocks in a distributed system, the input space is huge. And our assumption is that delay mechanisms in the deep path are hardly triggered in normal usage or testing, and therefore may have more timeout bugs. Then we use a deep priority guided algorithm for selecting delay sequences that can trigger newfound deep delays. In this way, Chronos constantly generates high-quality delay sequences as test inputs, and explores as many deep delay blocks as possible. The third challenge is how to execute delays. In real-world distributed systems, timeouts are typically set between 1 second to 10 minutes. However, injecting such long delays directly can significantly slow down the testing process. To address it, we propose a transient delay mechanism that directly sets the timeout value to 0. This enables quick triggering of delay logics in the system and speed up the testing process. We have implemented Chronos on 4 widely used distributed systems including Zookeeper, MySQL Cluster, HDFS, and Go Ethereum. In total, we have detected 28 new bugs in these systems. We compared Chronos with other state-of-art methods for fault injection technologies, including random method, brute force method, and coverage-guided fuzzing. The results show Chronos always outperforms others on all 4 targets distributed systems. To evaluate the effectiveness of the transient delay, we also run Chronos-, the version of Chronos which disables the transient delay and executes the actual delays. In conclusion, Chronos can detect all 28 bugs within 24 hours, while Chronos- only detects 14 of them, and Chronos covers 18% more delay blocks. Our future work mainly focuses on the following points. First, we would explore more oracles such as privacy leaking problem or performance issues to further improve Chronos's bug analyzer. In addition, we will try to enhance Chronos with finer feedback guidance in finding more timeout bugs. At last, we will try to adapt Chronos to more distributed systems. Thank you for listening. Please contact me if you have any questions.